Well, hello again. We're going to continue where we left off with section 10.1, comparing two proportions. So chapter 10 is basically split into two sections, comparing two proportions, and then in 10.2 we'll be comparing two means. Here's what we're going to work on for the next 2 days. So let's start by thinking back to what we learned in chapter 7. When we were looking at the sampling distribution of the difference between two proportions. Back in chapter 7, we said that the shape of a sampling distribution will be normal if n times p and n times 1 minus p are both at least 10. We said that the sampling distributions of p hat is centered at the true parameter p, and we said that the spread is going to be equal to the square root of p times 1 minus p over n if the sample is no more than 10% of the population. And we're going to use those facts today. But we're going to look at what happens to a sampling distribution that is the difference of two proportions. So this would be, just if you had a sampling distribution of one proportion. So what we're going to do is we're going to look at two populations that we actually know the proportion, the true proportion of successes. So let's say this is true. There are two schools, and at one of the schools, school number 1, exactly 70% of all their students did their homework last night, and at school number 2, exactly 50% of all their students did their homework last night. Let's say somebody at school 1 takes a simple random sample of 100 students at school 1 and records what proportion did their homework. School 2 does the same thing, but a simple random sample of 200 students from their school. Now, at school 1, they probably are going to get something close to 70%, and at school 2, they're probably going to get something close to 50%, but not exactly those numbers. But what can we say about the difference if they call each other and find, okay, what's going to be the difference in our two samples? So what happens? What can we say about that? Well, let's simulate it. So somebody used software to simulate doing this 1,000 times. So here is all of the different 1,000 different samples of size 100 from school 1. Here are all 1,000 samples from school 2. You'll notice they both kind of have a normal shape, centered where we'd expect at 0.7 and 0.5. But this distribution is the one we're going to focus on over here. This one is the difference between, for example, in one case, I might have gotten this result right here from school 1, and I might have gotten this result right here from school 2, and then when I subtract them, I get, this result right here. Okay? If you do that 1,000 times, here are all the differences that you get from those 1,000 different simulations. So what can we say about this approximate sampling distribution of p hat 1 minus p hat 2? Take a look at where it's centered. Well, it's at 0.2 because that's the difference in those two. That's pretty obvious. But you'll notice this is like how spread out it is. It's standard deviation. How is that related to these two? Well, let's think about this. P hat 1 and p hat 2 are actually both random variables because they can take on different values. So the statistic is the difference, p hat 1 minus p hat 2 is the difference between these two random variables. In chapter 6, we learned that for any two independent random variables, you can find the mean difference by finding the difference of the means, and you can find the variance of their difference by adding their variances. Therefore, when the random variable is a p hat, that means that the center of the sampling distribution of p hat 1 minus p hat 2 is equal to p1 minus p2. And you can find the variance of the sampling distribution by adding the variances of the individual sampling distributions for p hat 1 and p hat 2, which we had a formula for those that we reviewed right here. So basically I'm going to use this formula for p1, and I'm going to use the same formula again for p2. That gives me that and that. Notice that we're squaring them, which gets rid of the square root. And then, well, To find the standard deviation, you take the square root of the sum of that. And there you go. That's the formula for the standard deviation of the difference of two proportions. So here's what we know about the sampling distribution of the difference between sample proportions. Go ahead and press. Oh wait, for the shape, all of those have to be at least 10. Notice there's 4 different numbers to check, because for population 1, both of those have to be 10, and for population 2, both of those have to be 10. Otherwise, we already discussed those two, center and spread. Press pause if you need to take notes. I'm going to move on. Here's a picture of what that means. Centered at the difference, standard deviation. That's what the sampling distribution looks like. So let's take a look at an example here of these two schools. So each of these are large schools with more than 2,000 students. At school 1, 70% did their homework. 50% of students at school 2 did. School 1 takes an SRS of 100. School 2 takes an SRS of 200. After meeting, this is the result they get. They get that the actual difference was 10%. So maybe, I don't know, school 1 found 65% and school 2 found 55 maybe, or maybe it was 72 and 62, or it was, I don't know what numbers, but they had a difference of 10. What would the shape, center, and spread be of the sampling distribution? Well, we just kind of went over that. So we checked that all of these things are 10. N1 times P1, so it's 100 times 70, that's 70. And then 100 times 30, that's 30. Then 200 times 0.5 and 200 times 0.5, both of those are 100. All of those are at least 10, so the sampling distribution is approximately normal. It's going to be centered at the true difference in those, which is going to be 20%. And the spread, well, we're going to use that formula. We plug those numbers in. It's the square root of, there's P1 and 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Do the standard deviation of that, you get 0.058. Next, if this is what they actually got, how likely is that? So find the probability of getting a difference that's 10% or less. So what we're going to do is we're going to find the area to the left of 10% right here on this sampling distribution we just described. One way to do that is you can find the z-score for 10% and then use table A and look up the area to the left, or you can use our good old friend normal CDF. So normal CDF of negative, really negative number up to 0.1 for a distribution centered at 0.2 with a standard deviation of, what did we get? 0.058. So I find the area for that distribution, you'll notice, is about 0.04, about 4%, and that's exactly what table A gives as well. So that tells us that there's only about a 4% chance of getting a value that smaller if this right here and right here is what's true about these schools. So does that result, that 4%, give us reason to doubt the reported values? Well, 4% isn't very likely, so it does seem suspicious. That's it. That's what we can say. It's pretty rare, so we're not sure what's going on. It seems suspicious. One of our assumptions might be wrong. Now that we've talked about the sampling distribution, we can apply what we know about sampling distributions to create confidence intervals. So let's say I wanted to create a confidence interval. Okay. Now, if we don't know P1 and P2, then our best guess is going to be what we found in our sample. So basically what we're going to do is we're going to use this same formula, statistic plus or minus critical value times standard deviation of statistic, but we're going to use this as the standard deviation, and for the statistic we're going to use what we found in our sample. So when we do that, we get the following. I'll just jump right to the end there. So notice that since we don't know P1 and P2, we use P hat 1 and P hat 2 as our best guess. And again, since we don't know the actual P1 and P2, we use P hat 1 and P hat 2 as our best guess. So that right there is the formula for the confidence interval for the difference in two proportions. So if you think about this now as a new inference method, you can see here we have conditions to check as well. So we've got a random condition. Both of them have to come from random samples. Normal condition, there are 4 different values now we need to check that are at least 10. Now for independent, there's a few extra things to do because both the samples or groups themselves have to be independent from each other, and the individual observations within each group have to be independent. So like school 1 and school 2 have to be basically independent of each other, and then also people at school 1, individual students, have to be independent of each other as well. So let's say I'm going to do the 4-step process here to create a confidence interval for this situation. There were 2 surveys in late 2009. First one asked 800 U.S. teens about their use of social media on the internet. Second one posed similar questions for 2,253 U.S. adults. So 73% of teens and 47% of adults said they use social networking sites. So obviously, teens use social networking more, but let's construct a confidence interval for how much more do they use them. So here we go. State, plan, do, conclude. State for a confidence interval. We define our parameters. P1 is the proportion of all U.S. teens who use social networking. P2 is all those adults who use social networking. And we wish to estimate the difference, P1 minus P2, at 95% confidence. Plan, we state our inference method. This is called a 2-sample z-interval for P1 minus P2. We check our conditions. Random condition, yes, both came from random samples. Normal condition, we check that the number of successes and failures for each of those is at least 10, so that's 4 different values we have to check. So you can see, boom, 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 boom. All 4 of those numbers are at least 10. Now for the independent condition, we've got, you can see 3 different sentences here. The groups have to be independent. So teens and adults, basically they can't overlap. Yeah, there are 2 different groups. Individual responses also have to be independent, which is reasonable to assume. And then the 10% condition for both groups. Now that we've checked conditions and confirmed, we can move on to the do portion. You can plug in all the numbers into that formula and you get this interval right there. Ta-da! And our conclusion, you should know how to do this already. We're 95% confident that the interval from 0.223 to 0.297 captures the true difference in the proportion of all U.S. teens and adults who use social networking sites. This interval suggests that more teens than adults engage in social networking by between 22.3 and 29.7 percentage points. Obviously, there is a way to do it on your calculator. It's called a 2-prop z int. That's a 2-proportion z interval. It's under stat test. 2-proportion z interval is what I'm looking for. 2-proportion z interval is right there. 2-proportion z interval. And all I need to do is type in the number of successes and failures in each group. Boom, I just typed in, well, these are the successes and then the sample size, successes and sample size for the 2 different groups, confidence level 95%. Hit calculate, and there's my confidence interval right there. Same interval I got right there. And again, if we're going to use the calculator only method, make sure you blah, 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 blah. I say this every time. There you go. That's it for this part of section 10.1. We will finish 10.1 tomorrow.